So we'll come down here, and let's see something while I'm at it. Close this. You also have a, hey Dan, were we talking about somebody named Brady last night?
Yeah, that's the guy.
There he is. I noticed that this file has a 2004 creation date, so this file comes from the original manual. To the best of my knowledge, this is still accurate, appropriate. And Kyle, I think you asked me how we did temperature or some such thing, so here you go. We'll go over it a little bit in any event. So there's our equation, remember, how we compute temperature. And basically what we said, to make a long story short, is there's some equilibrium temperature which represents a temperature in the water at which there's no exchange with the atmosphere. You know, it's the temperature which is equilibrated with the atmosphere. And the change in temperature is proportional to the difference between the actual temperature and this equilibrium temperature. And it can go either way. You know, the water can heat up or cool down. And then there's a rate constant, KT. KT is the units of KT, I think, are watts per meter squared. So, yeah, oh, there it is. KT, watts per meter squared per degree centigrade. So this rho CP, what we've got to do is to take watts and, you know, divide by the specific heat of water to make it equivalent or make it appropriate for our model variable, which is temperature. So your goal, if you will, and, you know, we'll go over this, we've got to derive from meteorological observations the equilibrium temperature and the heat transfer coefficient, KT.
Before you go again, question. Is that equation appropriate for fresh water? And the reason I'm asking is you have the density of water at 1, and I'm wondering if the density of water, you know, for salt water changes and that you actually use.
I don't do that. I guess it would have a small
small impact.
A small impact.
But I just wanted to make sure I understood conceptually what you're doing. Okay.
Yeah. Okay. So you've got a program. We'll look at it in a few moments called Make Daily Hex Heat Exchange. So it takes raw meteorological data, and it will create a water quality model MET file. Inputs, dry bulb temperature, wet bulb temperature, dew point, wind speed, fractional sky cover. It also needs latitude. At this moment, latitude is hardwired into the program for Chesapeake Bay. So if you want to take this and apply it in, I don't know, Michigan or something, you're going to want to go into the program and make some changes. But fair enough. Some of these things are obtuse, but they tend to be the way that this data is reported. So you can get meteorological data from a number of sources. Most lately, we get it from the Air Force. On the other hand, I worked for the military, so you might find it from a different source. But for example, fractional sky cover is reported, I don't know how on earth they do this, in eighths. So if you see fractional sky cover as 4, it's actually 50%, right? It's 4/8. And the program deals with this. But if you get it from a different source, and maybe if the fractional sky cover is reported as something else, like actual percents or something, beware. You know, you want to go into the program and take appropriate measures. Wind speed, I'm surprised. That says 7 meters above the water surface. I thought it was 10, frankly. I either made a typo or my memory isn't as good as it used to be. That's how we're going to compute evaporation and heat transfer. Wind speed measured at an appropriate height. So if the wind speed is measured higher or lower, you either need to make a correction or, you know, assume that you're not going to worry about it. But again, I know when I first applied this a long time ago, 40 years ago, 1974, something like that, I actually had to, I fit like a parabola to the wind speed and corrected it to the appropriate height above the water. Dew point is, what is that? It's the temperature at which the amount of moisture in the air would start to condense. You'll get these from the Met data. I probably am not going to explain what they all are, but I will say these are the inputs to the program. I don't think we use wet bulb anymore. As a matter of fact, yeah, it's relic, but it's in the read file. It's been there for a long time, so give it any number you want, but don't lose this slide, right? Okay.
So evaporation is also calculated?
It's calculated.
But is it actually just for the purpose of calculating water temperature, or actually will take water out from the surface?
Does not take water out.
Okay, just for the purpose.
Just for yeah. Hey, look at that first bullet. Your biggest headache is finding a consistent data set that extends for the duration of your simulation. Seriously, this is a problem. And we've had. Recall that we're doing a 30-year. We've done at least a 25-year simulation, and just for example. I use Patuxent Naval Air Station, and a fellow who used to be here at the Bay program used a different station for the data that he put together. And I could actually look at the model and see something's different, because he used a very different wind speed, and I could see that things were different. And Richard and I have gone back and forth. So it's really a pain in the neck to get a consistent data set. I've also had problems, just old war stories. There is a station over on the Eastern Shore where they measure daily solar irradiance, those Einsteins per day that you're just craving to get hold of. And I used that for a while, and I looked and I found out that there was tremendous drift in those measurements that declined over the years. And I think they fixed it. But if you just use those raw measures, you were going to have some interesting impacts. So keep an eye on this sort of thing. That's...
One other question. Whatever station you pick, this MET file that you're creating applies to the entire system. Is that correct? Right. Okay.
Yeah, we had some questions about that. In the hydrodynamic model, wind is really crucial to computing surface shear stress, and I think the hydrodynamic people, they actually get MET data from many different stations and interpolate it and apply it to each individual cell in the grid. We don't go to that level of detail. We can't really go to that level of detail. You could average a bunch of stations if you liked. I know now there are now buoys out in the bay that measure wind speed directly over the water. So on the other hand, they don't measure these other things like dew point and I don't believe they do. They don't measure irradiance. So you could get the wind speed directly over the water now, but you'd probably have to combine it with data from a land station. And these are sort of decisions you're going to have to make. A long time ago, we actually had a small data set of wind speed measure over the water. This was going back 30 years, and we found it was about 1.5 times the wind speed measured at Patuxent. So this program is hardwired to take the wind speed measured at Patuxent Naval Air Station and multiply it by 1.5. Don't lose this slide, right? Either don't lose this slide or be careful how you use that program. Yeah. Be careful of sky cover, the program uses eighths. And again, it does that because the Met data that we had reported sky cover in eighths. I just can't imagine some fellow walking out of the control tower up at Naval Air Station and looking up and saying, yup, it's about 2/8, you know, right? You know, don't look at me. It just, okay.
Carl?
Yeah.
If light bulb temperature is a relic, how do you get humidity for the?
I think from the dew point.
Oh, you have the dew point, that's right.
Yeah.
I understand. I missed the dew point.
For your Met data, so that's all, even air temperature is from the DoD source?
Excuse me?
All your Met data from Patuxent Naval Air Station, that's from the military source. Okay. So I found the Naval Air Station data from NOAA. It looks slightly different. So.
What would I say? Your problem is finding a consistent data set. You know, I can't, I would believe you, but other than that, I can't say anything.
Do you know how to get a hold of military sources?
I don't know if you can.
Okay.
You know, we had a very convoluted process where we made a official request to the Air Force and got the data. I'm being serious. I don't think you can. And why the data that's provided by the Air Force might be slightly different than what's provided by NOAA or something like that, I can't say either.
Also, Carl, I think the real data, initial data, are recorded with a high frequency. In a couple of minutes, you know, you have a lot of data. Data I send it to you, I think in Carl or ping, is calculated kind of every day. I think it gives you daily, right?
Yeah.
This after a lot of processing.
Yeah.
And there's some you know, they do not, it's not a regular because sometimes they miss the record. It's not every 10 minutes, you know, sometimes 7 minutes or 1 hour. So yeah, it's a lot of
Thanks.
Yeah, I guess you're looking at climate change. You know, these are the things you have to deal with when you have messy data. Okay, so what comes out of the model is surface heat transfer coefficient, that KT, the equilibrium temperature, the photosynthetically active radiation, the fractional day length, and the wind speed. The wind speed kind of goes in and comes out, but if you choose to use that reaeration formula where reaeration is based on wind, you need the wind speed. So it goes in and comes out. Fractional day length, that has to do with, remember what we did was we took the total irradiance and we fit a sine wave over the daylight period. So fractional day length is, you know, the daylight period varies a little bit from winter to summer. What we do, we compute the solar radiation in, I guess, watts. You can compute this to a fairly high degree of accuracy based on things like air temperature and cloud cover. We compute that and then we convert it to these magical things called Einsteins. If you had a really reliable record that you felt good about, you could use that reliable record. As I mentioned, when I looked personally at the long-term monitoring data, I found there was a lot of drift in it and I didn't think it was suitable. I hope that's been corrected and maybe now it's suitable, but again, you'll want to look at these and consider these things. But what I'll say is, for the Bay model, right now, the solar irradiance that the phytoplankton use is computed from solar radiation. Watts is a measure of energy, thermal energy. The Einstein is a count of photons of photosynthetically active radiation. So it's a funny, who counts photons? I don't know. But in any event, as I showed you empirically, and I don't know if I have that graph anymore, these can be related. So this is what we do. Let's see. Okay, well, some of the things I just mentioned. So the photosynthetically active radiation is derived from computed daily average solar radiation. It's empirical. If you have observations, you can substitute them. You know, this is just things I mentioned already, so we won't spend a lot of time on that slide. This is an equation that I use to fit that that sine wave to the daily total. It's built into the model. You don't have to worry about it at all. You know, it'll be taken care of. Okay, so we'll look at this.
So when you do the irradiance, are you including the cloud cover in the prep?
Yeah.
Okay.
Okay, so as I mentioned, my very first job was modeling power plant cooling ponds, and to do that you had to be really good at your temperature calculations. And at the time, my Bible was this publication by Edinger. I think it's down here. There it is, Edinger, Brady, and Geyer, Heat Exchange and Transported in the Environment. I've carried that book with me for 45 years, wherever I go, and even when I've retired and cleaned out my office, I held on to that, you know. So if you really want to know the details, this chapter reports, but basically it says we use this equation, we use this equation. If you really want to know what's behind it, get a hold of that. It's a classic, you know. I just don't know if anything has come along that is better. So,
So Carl, does the hydrodynamic model use the same algorithm for heat transfer?
It does, to my knowledge, yeah. Although I don't know if they use this program to derive the KT and TE. Okay, the major thing about this heat transfer, I'm not going to go over every equation, but the elements of surface heat exchange are solar radiation. Okay, so the sun shines and it warms up the water. Some fraction of that is reflected back, and this is more or less taken care of. But, you know, it hits the water, some fraction is reflected, some fraction heats up the water. Atmospheric radiation. This is, you know, you think of the sunshine, you think, well, how does the atmosphere shine? But we're talking about black body radiation. The atmosphere has heat, and that creates thermal radiation. There's back radiation. Because the water has temperature, it also radiates heat. There's evaporative heat loss and conductive heat loss. Evaporative heat loss, the reason we compute evaporation is when you have evaporation, you lose heat. You know, that's fair enough. And conductive, conductive is actually direct transfer of heat between the atmosphere and the water body. You go through a lot of equations, and most of it, as I said, most of it comes directly from that Edinger, Brady, and Geyer report. And, you know, I don't need to go into details of the radius vector and this sort of thing. But